Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In this video, we're going to move to the second statistical property, the one that gives us the actual expression for the variances of the OLS estimators. Now, these two formulas that you see right here might at the beginning sound a little bit too difficult to remember, but ultimately you will have to remember, especially the formula for the variance of the beta 1 of the slope. Now, why do we need the second property and why is it so important to talk about it? Well, we always need to think about, now that we have figured out that our OLS is unbiased, how precise it is, this estimation that we are doing. So while the unbiasedness, which is our first property in here, is more about accuracy, the second statistical property, the variance, is more about precision. Okay? And we are going to learn the intuition behind what this formula of the variance of the beta 1 hat especially means for us. We will also complement it by reiterating once again what the assumptions that we need to get to the statistical property is. So for the first statistical property in the previous video, we showed that we need 5 very important properties, which include linearity, random sampling, variation in X, the zero conditional and unconditional mean. For the second statistical property, we are going to use one more assumption from the ones that we have looked together, and that is all assumptions 1 to 5 plus the homoscedasticity assumption. Okay? Together, all of these are essential to making sure the second statistical property is fulfilled, with the highlight obviously on the homoscedasticity assumption. So let me give you a little bit of an intuition first on what the variance of an estimator means, and then we'll move into what exactly does this mathematical expression introduce to us. Think about a case scenario where, let's say, this is where all the observations that you have for a particular population is. Every time you take, let's say, a random sample here, you will run an OLS, and you will get a beta 1 hat. Then let's say you take another sample and you run an OLS, you get another beta 1 hat, and you keep taking random samples from your population all the time, and you're literally getting this, if you were to put them in your spreadsheet, a list of all the beta 1 hats that you have estimated. Okay, now the thing is, because you're picking different random samples, the betas that you are estimating are slightly different from one another. So all of them, hopefully, if you've done everything correctly, should give you a beta hat that is close to the truth, meaning to the true beta. But some samples might give you a beta hat that is actually a little bit far off from the truth. So if, let's say, you have this whole list with the ones that go close to the truth and the ones that are far from the truth, how much of a variance do you notice in all the estimations of the beta when you have these repeated samples? And the rule of thumb will obviously be that if you have a low variance, that means that your estimator is stable and precise. However, if you have a high variance, it means that your estimator, I'm going to put it into quotation marks here, but jumps around. So what does it mean? It's not as precise as we might want. So obviously we want an estimator that has a low variance. So even if we miss 1 or 2 times the being close to the actual true value of the beta, we are still close enough and we are not jumping around too much. Okay, so this is the whole reason why we care so much about the variance of the beta null hat and the variance of the beta 1 hat. Now that we have understood a little bit the intuition of like, why do we need to talk about the variance? Let's go back to the variance formula that we had earlier. I will be concentrating mainly in the variance of the slope, the beta 1 hat, because that is the one that is the most important. And let me rewrite it once again for you here. We have this sigma square divided by the sum of xi minus x bar all squared for I going from 1 to n. So very clearly, we can see that our denominator here is an item that we've seen quite consistently throughout all of the videos. And obviously, this gives us just the variance of the x formula. Okay, if you are wondering where is this then sigma square coming from, well, that is mostly from the population, from the error term. Okay, now based on all of these elements that we have in here, what are the key takeaways that we can have from this formula? The main key takeaways are the following. When the variance of beta 1 hat is high, which remember, this is something we don't particularly like, it means that we are less sure about beta 1 hat being close to beta 1, meaning the true population. The second parameter, the second key takeaway is that if the sigma square, so this variance is quite high, that means that also the variance of the beta 1 hat is going to be high, which sort of makes sense. Like if you don't know a lot of what is going on in your population, and it means like there's still a lot of noise that exists out there into explaining the variation in your y through the x's that you have chosen, it's just going to mean that your beta 1 hat is going to jump around quite a lot because it's not going to be able to get all of that, to explain all of that variation. Okay, and the last main key takeaway is obviously that if the variance of your x is high, then the variance of your beta 1 hat is actually lower. So what does that intuitively mean? Think about it this way. The more different values that you have across your x variable, the more patterns you might, or well, patterns is probably not the best word, but the more you will be able to explain about the changes that you will see in y based on like all of these different variations that you see in the value of the x. So having x having a lot of different values and then seeing how they connect to the different values of y that you have, it's going to be a lot more informative than you simply having 2 or 3 values of the x and then having 10 values that you see on your y variable. Okay, so this is a very important key takeaway, and it's also something that might come up very likely in exams where they ask you, well, what could be the things that you could do in order to make sure that you lower the variance of the beta 1 hat. Okay, so keep in mind, in an indirect way, especially, what this last key takeaway is telling you is also that larger samples will have more precise results. Okay? So we have finally seen both the intuition on why it's important to talk about the variance and the intuition of like what this formula gives us. Before I conclude this video, I'm also going to give you the variance of the formula in matrix form, since we're always giving both the scalar and the matrix form for everything we've been doing. Keep in mind the variance of the beta 1 hat in matrix form, and obviously we're going to do that conditional on the x in here, is going to be sigma square, and then we're going to have x prime x inverse. If you are worried, like, well, in the books or the slides that I have, I don't see these one in here. It's just the variance of the beta. It's also completely fine and actually preferred that way, because since we're working with matrix forms, we are basically estimating the variance of all the betas in one go. Okay, that's why we liked the idea of working with matrices and the matrix notation. Okay, if it's still unclear where this sigma square is coming from, and the reason why I didn't really concentrate much on it, it's because we're going to talk about it a little bit more as we talk regarding the third statistical property, which actually will give us an expression for that sigma square. But until then, keep in mind that the whole reason why we could get to this formula was because we added the homoscedasticity assumption. And if homoscedasticity holds, then this formula and also the formula for the variance of the beta null hat will stand. If the homoscedasticity assumption does not hold, you will not then be able to get these exact formulas that you have seen here. Thank you for following for Statistical Property 2, and I'll see you in the next video with Statistical Property 3.